Hi everyone, welcome to another session of the HPL files. Today we will be solving a problem about simple harmonic motion. Let's begin. In this problem, we have a figure that shows a turntable with a rod attached to it at a distance of 15 centimeters from the center. The turntable is illuminated from the side so that a shadow is cast on the screen. As you can see here on the figure, a simple pendulum is placed behind the turntable and is set oscillating so that it has an amplitude equal to the distance of the rod from the center of the turntable. The speed of rotation of the turntable is adjusted. When it is rotating at 1.5 revolutions per second, the shadow of the pendulum and the rod are found to move back and forth across the screen exactly in phase. That means when the rate of rotation of the turntable is this, the shadows of the pendulum and rod are actually moving together. For the first question, we are asked to write down an equation to describe the displacement x of the pendulum from its equilibrium position and the angular frequency of the oscillation of the pendulum. To answer this question, let's look at the given information in the question. First, we have this distance. This distance is actually the amplitude of the oscillation. So let's write it as A, or x of 0, is equal to 15 centimeters. We are also given with the rate of rotation, which is 1.5 revolutions per second. Note that one revolution in this situation is equivalent to one complete oscillation of the pendulum. That means the frequency will be 1.5 hertz. Now, when we are describing simple harmonic motion, we can use either a sine curve or a cosine curve. But that depends on where you start measuring the motion. Here, we will start at the equilibrium position. So let's use sine. Let's use this equation, x is equal to x sub 0 sine omega t, where x is the displacement at a given time t, x sub 0 is the amplitude, and omega is the angular frequency. The angular frequency can be rewritten as 2 pi f. Substituting the given information or values and simplifying the equation, we'll have x is equal to 15 sine 3 pi t. This is the equation that describes the displacement x at any given time t, where 3 pi is the angular frequency. Next question. The turntable rotates through 60 degrees from the position of maximum displacement shown in the diagram. Let's first calculate the displacement of the pendulum at that point. To properly label the angle, let's follow these guidelines. This is the position of maximum displacement. Then the turntable rotates through 60 degrees. That means the new position of the rod will be around here. Marking that position, we'll have this red guide line. And we are asked to calculate the displacement from the equilibrium position. The equilibrium position is denoted by this vertical line. So the displacement that we are supposed to get will be this one. Let's now write down the given information in this part of the problem. We have the theta or angle to be equal to 60 degrees. And then let's utilize the general equation for the displacement x. Substituting the value for the amplitude, we'll now have x is equal to 15 sine omega t. Now, omega, or the angular frequency, can be expressed as the angle divided by the time. Now, take note, this angle should be in radians. Manipulating this equation will now have the angle is equal to omega times delta t. Now, if we start with time is equal to 0 and angle or initial angle to be 0 degrees, then this will reduce to theta is equal to omega t. That means you can replace omega t here by theta. We now have x is equal to 15 sine theta. Now, let's convert this theta to radians, since the angle that we should use for this equation should be in radians. 60 degrees will be equivalent to pi over 3 radians. Now, the next question is this. Is this the angle that we should replace or use in this equation? Now, look at this part, sine theta. If we get the sine of 60 degrees, we are actually getting this side. But we are supposed to solve for this side. Since we're using sine and we need to get this, the angle that we should consider is not the angle measured from the maximum displacement, but actually the angle measured from the equilibrium position. And that will be 30 degrees. Converting 30 degrees into radians, we now have pi over 6. This is the angle that we are using. Substituting that angle, we'll now have x is equal to 7.5 centimeters. That means this displacement corresponds to 7.5 centimeters. Next, we are asked to calculate the speed at that point. So listing down the given information, the amplitude, the point in consideration, and the angle from the equilibrium position. We can solve the speed at that given point using two different equations. The first equation will be this. The product of omega and the square root of the difference of the squares of the amplitude and that specific displacement. Substituting the given values, we'll now have the following. Remember that omega, or the angular frequency, is equal to 2 pi f, and in this problem, it's equal to 3 pi. We'll now have a speed of 122 centimeters per second. The other formula that we can use to solve for the speed is this one, where v sub 0 is the maximum speed. Now, how do we determine the maximum speed? Remember that in simple harmonic motion, the object will have a maximum speed when it is passing by the equilibrium position. Since x is the displacement from the equilibrium position, and the object is at the equilibrium position at that given time, then x will be equal to 0. Which means the maximum speed is given by omega times x sub 0. Now, omega t over here is simply this angle. Substituting the given values, we now have the following, and evaluating this, we will obtain the same value for the speed, 122 centimeters per second. Next, through what further angle must the turntable rotate before it has this speed again? Now, looking at this given figure, the speed was determined when the turntable made this rotation of 60 degrees. Now, if, say, for example, the pendulum will now be on the other side of the equilibrium position, we can find that equivalent displacement in the rotation of the turntable to be this one. Now, marking that position, this will give us the following angle. Notice that what we are looking for is that the angle through which the turntable has rotated in order to reach this specific point. Looking at the given figure, it's easy to see that these two angles are both 30 degrees. That means the angle that the turntable must rotate in order to reach this speed again will be equal to 60 degrees, or pi over 3 radians. So that's it, guys. I hope everything's clear. Thank you for learning with me today, and see you on the next session of the HBL files.